Not long after, we realized that wavy light can actually act like a particle, a photon with a certain energy. A guy named Louis de Broglie asked, well, is it possible that a particle, just any old matter particle, an electron, a proton, a whatever, a human flying through the air, could act like a wave? And he did a little fancy footwork with the math, and he realized that if this were true, right, and there's a way to prove this, but I'm not going to get into it right now, but if matter particles really did act like light waves, then the wavelength of a matter particle, or of a matter wave, the wavelength of a matter wave would be Planck's constant over the momentum of that matter particle. In other words, the wavelength would be equal to Planck's constant over mv. Remember, momentum is mass times velocity. Okay, now, this was a breakthrough discovery, and we're going to see why in a second. But this really gave birth to this understanding of quantum mechanics in the material world, not just within the quantization of light, but within, all of the material world. And there was a way that we went about proving this, and I'll get there in a second. But first, I want to kind of just get some practice exploring this relationship for a second. And I want to explore this idea of what would be the quantum wavelength of like a thing that's macroscopic that we can see with our eyes versus something microscopic and very small. So let's take the quantum wavelength of a white dove versus an electron. All right. So this is to answer the question that may be on a lot of people's minds, which is, why exactly is it if matter particles also have wavelengths, why don't I see them, right? Why, when Scott's running across the room, do we not see a wavy Scott? All right. The answer to that question is going to be revealed through this problem. All right. So let's start with the dove. With this dove, we know that the wavelength of the dove is going to be Planck's constant, which is 6.6. We'll just make it a little bit easier, which is, for now on, just do 6.6 times 10 to the minus 34 joule seconds. And, a typical dove is, let's say, around a kilogram, maybe a little bit less, but let's do just orders of magnitude here. And, this problem says that dove is moving at 100 meters per second, right? What would be the wavelength of that dove? And I get about 6.6 times 10 to the minus 36 meters. People, that is tiny. It's a wavelength that we would never be able to actually perceive. All right? Now, let's look at it from the perspective of the electron, right? So an electron, let's say we have 6.6 times 10 to the minus 34 joules times seconds. And now the mass of an electron is much smaller. It is going to be 9.1 times 10 to the minus 31, right? And this one's also moving at 100 meters per second. And so in this case, I get 7.2 times 10 to the minus 6 meters, or 7.2 micrometers. Still not visible to the human eye, but much, much bigger than something that's flowing in the actual world, right? And something that has like the mass and momentum of a dove or a person or anything that we would actually see in the world. That's why we don't see quantum mechanical effects in the world. That's why it went hidden for so long, why it took us so long to actually discover this. But when we're talking about the subatomic world, then quantum mechanics shows up a lot because we're dealing with very, very small masses. And those small masses mean that you have reasonably large quantum wavelengths. All right, and we're going to talk more about the interpretation of those quantum mechanical wavelengths. So one misconception question I'd like to do right now. When you throw a baseball, Its de Broglie wavelength is the same size as the ball, about the same size as an atom, about the same size as an atom's nucleus, much smaller than the size of an atom's nucleus. Okay, so again, we can use this value as a reference, right? This would be around the same quantum wavelength as a baseball, because a baseball, you know, it's not that much different in mass than a dove, for example, okay? And this times 10 to the minus 36, is that about the size of an atom's nucleus? Well, an atom's nucleus is like times 10 to the negative 12, roughly-ish, okay? You could see that the quantum wavelength of something like a baseball is actually much, much smaller than an atom's nucleus. Again, something that makes it absolutely insignificant for us in the macroscopic world over here. Okay, so in the next video, I'm going to explore how we actually ended up proving that there is this whole quantum wavelength for material objects. And I'll give you a hint. You've seen it before, and if you pause and reflect, you might yourself be able to guess how you could prove that material particles have a wavelength. Challenge yourself.